everybody, today I'm going to talk to you about the article called Temperature Dependence of Entanglement and Coherence in Fenna Matthews Olson Complex Using a Fret Initial Condition by Bruno Gonzalez Soria and Francisco Delgado. First, the Fenna Matthews Olson, or FMO, is a light harvesting protein with close to 100% efficiency. It transfers energy from the chlorosome to the reaction center, passing through the bacteriochlorophyls that it holds within its protein scaffold. Here in the left we can see one of its 3 monomers holding its 8 bacteriochlorophyls and their dipolar momenta. On the right we can see the energy flow of this excitation energy going through the entrance bacteriochlorophyls that are the higher energy level bacteriochlorophyls, which are bacteriochlorophyll 8, 6 and 1, going down to the lower level energy level bacteriochlorophyls, which are bacteriochlorophyll 3 and 4, from where the energy is finally transferred to the reaction center. Due to the large number of atoms in the protein, it's normally modeled as a continuous regime of oscillators working additionally as a thermal bath. Here we see how the total Hamiltonian is built by the Hamiltonian of the system, a Hamiltonian of relocation, the bath, and the interaction between the system and the bath, which fulfills the von Neumann-Liouville equation. In this article we use the Geom method, the hierarchical equations of motion method, which is a non-Markovian approach considering the memory of the system. It is constructed as D recursive equations, where D represents the previous temporal stages of the bath. Here you can see the terms that build up the Geom equation, considering the oscillation term, relaxation term, and energy sink, which are bacteriochlorophyls 3 and 4, where energy is finally going to be sent to the reaction center. Here we have some other non-Markovian parameters, and we go to the initial conditions. In this case, we're using a model of 8 bacteriochlorophyls and a depth of 3 for the Geom equations, and sweeping through these temperatures that you can see over here to see the effect of temperature in the entanglement. The initial conditions are defined by FRET, the forced resonance energy transfer. It is a mechanism which depicts the energy transfer between 2 light-sensitive molecules in the rate of the FMO complex global energies, then transferring such excitation to certain entry bacteriochlorophyls, and it is commonly written as you can see down here. These are the results obtained for the population evolution using a reorganization energy lambda of 35 cm to the -1 and a defacing rate gamma of 50 cm to the -1. You can see that excitation is located in bacteriochlorophyls 8, 1 and 2 due to the FRET initial conditions, and the bacteriochlorophyll 6, even though it was expected to be an entrance, one of the main entrances of energy, turns out to be a secondary reaction. We can see how energy flows as, remembering the previous diagram, goes from these initial bacteriochlorophyls towards bacteriochlorophyll 3. Bacteriochlorophyll 4 isn't very present in this using these initial conditions. Showing results for lambda equal to 65 cm to the -1, we see that the equilibrium reached for bacteriochlorophyll 3 happens much earlier at lower temperatures, even though it decreases as temperature increases. Measuring the entanglement of the system, we use concurrences, partially tracing the density matrix. Here you can see the concurrence for between bacteriochlorophyls, one bacteriochlorophyll interacting with another, and one bacteriochlorophyll interacting with the rest of the system. Coherence is the sum of all these concurrences, and is defined by the CL1 norm. Here you can see that 0 would be a separable state and 1 would be a maximally entangled state. Now here are the results of concurrence. These plots show in the center the CK, or the concurrence that has each bacterial chlorophyll with the rest of the system. We can see that in the beginning of the process, moving counterclockwise during the first 4 picoseconds, we see a high level of concurrence in bacterial chlorophylls 1, 2, and 8 in the beginning of the process, and a high level of concurrence in bacterial chlorophyll 3 by the end of the process. We are showing results for reorganizational energies 35 centimeters to the -1 and 65 centimeters to the -1. And finally, showing the coherence temperature dependence for both cases. We see fast and long-lived coherence is present for the larger reorganizational energy of 65 centimeters to the -1. The larger values of coherence are related with the lower temperatures. Interestingly, sudden initial peaks reported for other initial conditions disappear using the Fret initial conditions. And comparing both outcomes, we note that the large long-lived coherence is produced by such initial conditions. For concluding this presentation, I would just like to point out that a boost of long-lived coherences via localized entanglement was tracked using Fret initial conditions in the Helm method to model the dynamic evolution of one of the FMO monomers. Fret initial conditions reveal a different behavior to that of assuming a single entrance of excitation, like for example only the bacterial chlorophyll 8, and suggesting a more long-lived sustenance, especially for lower temperatures. Larger reorganizational energies boost the sustained entanglement between bacterial chlorophylls 3 and 4, faster establishment of entanglement in other pairs of bacterial chlorophylls, but more limited to low temperatures. And reorganizational energy values suggest an important role in the timescale and behavior of such coherence phenomena. Thank you very much. Hope you enjoy our article.